Hey students, thought I'd work out another solution for you. I got a question on this one. It's a really good question, and at first when I got it, because it's from the harder book, I thought maybe it was a tough problem, and it kind of is. So maybe that was the depth of the question, but also I realize that there's some unit conversion going back to chapter 1, so don't overlook that. But I also a little typo, which goes back to chapter 1. And so let me start there, right here. And I say chapter 1 because chapter 1 we had these things that we were asked to estimate. We had problems that said, approximately, what is the height of the ceiling in meters. And if you put like 3 or 4 meters, that was great. If you put 1 meter, you don't really understand what a meter is. That was the point back in chapter 1. Anyways, I could go on to other examples we did in chapter 1, but this is ridiculously high. I mean, this flow rate, this is 3.8 billion cubic centimeters per second. Now, a cubic centimeter probably, it shows up on the video, is probably about this size, okay? And can you imagine a billion of those? I mean, I'm not even sure how to describe that. Or maybe if you kind of visualize, and I know we're not in the classroom this year, but if you watch the videos, that little desk I have up there is about a meter wide. It's about a meter tall, and it's about a meter in length, and it's got a little kind of sink and faucet system here and enough room for my books. But that would be 100 centimeters by 100 centimeters by 100 centimeters. So that makes 1,000,000 cubic centimeters if we did all this in centimeters. So that's, a pretty good size volume. I mean, much bigger than the volume of a human. And you're talking about one capillary flows that, well, that's only 1,000,000, and this is 3 billion. So we would have to have 3,000 times the volume of that little desk in front of the classroom, which is many times my volume. And you're saying that's the flow rate in one capillary? No. So this is, like I said, a typo that is so bad that hopefully it's obvious, and that's what I'm saying going back here to chapter 1. And so, I mean, look at this radius. I mean, if you got this little tiny narrow tube and you're talking about this much volume, I mean, this has probably got to go zipping through here at, the speed of light or greater. I mean, it's just ridiculous. It would be like somebody back in chapter 1 saying, what approximately is the size of the ceiling? And you say, 1,000 meters. Well, no. I mean, no, it's just so ridiculous. Nobody's going to even jive at that. Anyways, so if you didn't notice this and you already worked on the problem and you're trying to get the right answer, this could be the problem. There's also, like I said, some unit conversion and a little bit of calculus here. But I think this could be a significant problem. So always stop and think about your numbers, think about what they mean, and that, it's kind of how I got started. And somebody sent this, and I just go, ooh, that doesn't even seem right. And it made me stop and think about it. And sure enough, I was like, oh, there's got to be something seriously wrong with that. So I redid this problem, or I guess I looked at this number, and I go, you know what, there's got to be like a -9 here. And go, let me recalculate everything with a -9. And it all matched the answers in the book. So the book has a little typo because of that. And so my, apologies. And actually, I should probably look on the more recent online one now that I mentioned that. But as long as I'm here, let me go ahead and work out the solution. But you know what? Now that I think about this, that's the nice thing about the online one. Some of you might not come across this if you do the online one. I had downloaded it, and yeah. So, like I said, you may or may not have that. I'm glad I kind of said that out loud. All right, but let me work out the problem. Otherwise, with or, without that typo. But I'm going to fix that typo. So as we read the problem here, it says the flow rate of blood through, and then here's the radius of the capillary, and then here is its volume, cubic centimeters per second. And then what is the speed of the blood flow? So let me put here A, and maybe kind of draw some kind of tubing system here. And maybe I'll take a section of the tubing. So here's the capillary. Here's the blood, a particular volume in that. And if you said that at this point within the capillary there is some area A and some length X to that blood, you would have kind of a cylinder lying on its side. And so you would say that the volume then is the cross-sectional area times the length of the cylinder. Yeah, that's probably the way to do it. Or maybe for cross-sectional area being a circle, you'll write this as pi r squared times the area. Now, here's where the step of calculus comes in. Let me take this equation and take the time derivative of both sides. And at least in this small area, what we'll say is that this length, or this r value, the radius, doesn't change. So I'll just kind of imagine a small little section of that moment in time, and the radius wouldn't be able to change by too much anyways. So I'm going to treat not only pi as a constant, but the radius also as a constant. And so as this flows along, the position x does change. And in fact, that then dx dt is the flow rate, velocity. Not to be confused with this, and we don't really have a symbol for the volume, and let me spell out at least the first three letters of volume so you don't confuse it with velocity. But then this would be saying, how does the volume change with time? So this is the flow rate. We might even call that a Q, where it's kind of standard symbol in the book. Okay. And so now looking at this and the question for part A, they give us the Q, the flow rate. They also give us the radius, and we should be able to figure out then the velocity. And that's the problem here. So let me put that in. They give us this flow rate, like I said, with a typo. So it'd be 3.80 times 10 to the minus 9 cubic centimeters per second. Then we have a pi, and the radius squared would be 2 times 10 to the minus 6 meters squared, and then times velocity. So now also talking about chapter 1, you can see we have a mismatch of our units. This side would be, of course, in meters squared, and then whatever units we want that to be in, and this is cubic meters. So I'm kind of thinking maybe the best thing to do is to convert this into centimeters, because a centa is this 10 to the minus 2. So that number there I will change into centimeters. So that what I will get here is a pi, and when I square the 2, I get a 4. When I square the 10 to the minus 4, I get 10 to the minus 8. Then I get centimeters squared times velocity. And what's nice about that is then over here, 3.80 times 10 to the minus 9, I will have centimeters cubed, which let me write it as centimeters squared times centimeter. So that centimeters squared cancels off. And now when I go to solve this for velocity, I'll have it in units of centimeter per second. So there's a little bit of play there with your units too. So like I said, two things really going back from chapter 1, the ridiculousness of this typo if it shows up on yours, and then also the unit conversion, and then of course probably the hard part is applying a little bit of calculus here to taking the volume formula and applying the derivative, and that's probably the hardest part of this step. So now let me actually then grab my calculator here and put in the 3.8 times 10 to the minus 9. Let me first divide that by a pi, and then also divide it by a 4 times 10 to the negative 8. And I get a 0.0302, and as I said, units of centimeter per second. And just to convert it into scientific notation, yay, there we have. And let me flip back to the answer here. Where is it? Scrolling. Number, okay, what did they get? Yeah, so, oh, good. Yeah, here it is. There it is. 3.02 times 10 to the minus 2 centimeters per second. And so you life science people know that, the capillaries is where the blood flow is deliberately set up to go very, very slow so that you can have a transfer of your materials, and particularly the diffusion of oxygen. And so this is, and carbon dioxide, I guess, going back and forth. But this is the flow rate. Very, very, very slow while it's in a capillary, and given plenty of time for things to diffuse. Now, part B then is an extension of this. Let's see, what does part B then say? Give you an idea that assuming all the blood in the body passes through capillaries, so as it cycles around, how many capillaries must there be in order to carry a total flow of 90 cubic centimeters a second? So I get the idea that that this is the flow, the amount of flow that is needed to flow through the human body to keep it alive and keep it functioning here. So given that we know that there's 3.80 times 10 to the minus 9 cubic centimeters flowing in one capillary tube, if we had 2, we would double that. If we had 3 capillary tubes, we would triple that. So let me just say we have n capillary tubes. So I don't know how many capillary tubes we have, but n times that would be the total flow rate, which they are telling me is supposed to come out to be 90 cubic centimeters per second, which is perfect because cubic centimeters and per second would each cancel off. And I'm going to end up at the end of this with no units, which is good because I just want a number. How many capillary tubes do you have? And so let me take the 90 and divide it by 3.8 times 10 to the negative 9. And we're looking, it looks like a roughly I'll call it 2.4 billion. So 2.4 billion capillary tubes. And looking up at the answer, yep, that's the answer they got, although they did do the 3 significant figures, so maybe I'll do that. I should, yeah, 2.37. So that's how many capillary tubes. I see that it does say this is an overestimate, but still kind of in the ballpark, kind of a reasonable number. Okay, hope that helps. Like I said, a little bit of calculus, that might be the hard part, a little typo, a little bit of unit conversion. Take care.